hand over to our speaker tonight, David Ashby from Worcester.
So I'm going to talk about archaeological geophysics and non-invasive survey techniques. So we're not talking about digging holes, we're talking about what we can find without digging holes. So the first question is, what is non-invasive survey? So it's the identification and exploration and examination of archaeological sites through the use of techniques which do no damage or disturbance to the subsurface remains. So, like I said, we're not going to dig holes, we're going to look at what can be seen through different techniques by just looking at the surface and looking at what's under the surface. And there's lots of different techniques that can be used. We're going to discuss some of them in detail. So we're going to look at geophysics in detail and different types of geophysical techniques and some of the problems with them and the advantages of them. You can use aerial survey, so aerial photography, so taking photographs with aircraft, something called LiDAR, which we're going to talk about a bit, and satellite imagery, so that might be like you see on Google Earth, but also thermal imaging, infrared spectrum imaging using satellites. Also topographical survey, so this might be where somebody walks across a landscape and looks at the features and the landscape features. Doing building survey, so this is manual, so physically going out with a tape and measuring things and taking photographs. And also 3D laser scanning, which we'll talk about. And then you can, borehole survey sort of comes into this. So borehole survey, we are going to make a hole in the ground, but we are only going to make a small hole. Anywhere between 5 centimetres round and about 20 centimetres round. But it's very good for doing landscape surveys. So if you're wanting to look at a huge landscape, you're not going to dig trenches across the whole of the Somerset levels, for example. But you could do a borehole survey, drilling holes looking at the past environment. So, start with geophysics. It's one of the main techniques. So, Gator and Gaffney are two big geophysicists in archaeology. If you've watched Time Team, they were on there. So their explanation for geophysics is the examination of the Earth's physical properties using non-invasive ground survey techniques to reveal buried archaeological features, sites and landscapes. So we're looking at what's under the ground by putting probes in the ground, detecting, but not digging. So the most damage we'll do is the same as aerating your lawn. So we have a few different geophysical techniques you can use. So there's resistivity and resistance imaging, which we'll talk about in depth, the same as magnetometry and fluctuating radiometry and ground penetrating radar we'll also discuss. There are a few other techniques, so there's magnetic susceptibility. This is a technique that's not used so much nowadays because it's quite long and drawn out. It doesn't take automatic readings. You have to put a probe on the ground and take a reading and then take an air blank and then put it on the ground again. Very good for using in trenches, things like that you can find very specific targets. You wouldn't want to survey a huge area with it. You use something called EMs, or electromagnetics. This is being used more, not as much as these first three techniques, but it produces its own magnetic field, this instrument, and you can look at the underlying archaeology. There's also sonar, so it's used in marine archaeology, sonar. So it is a way of detecting what's under the water. So if you're looking for shipwrecks or planes, etc. I think someone's trying to get in. Oh, I've got in. So the first one we're going to look at is resistivity. Resistivity is one of the most basic ways of surveying an archaeological site. So it's mostly produced by a company called Geoscan. They're based in Bradford. You can use it, so it looks like this. So it looks a bit like a Zimmer frame. You might have seen it on Time Team. You can use it in what's called dual probe or quad probe, mainly. So you have 2 probes in the ground, like this, or you have 4 probes in the ground, like this. You can use 3 probe arrays as well to do different things, so to look deeper or to do multiple lines at once. The survey technique works by looking at the difference in the ground's electrical resistance. So it works by sending a very small charge of electrical current through the ground, about 9 volts. So you're not going to get electric shock off of it. It's got an internal battery, so we don't have to plug it into the mains. And what you have is you have a fixed umbilical cord. You've got a fixed cable, and you have a set of remote probes that go outside of the area you're surveying. These are pinned into the ground. And you have a set of mobile probes on this frame that you move and you take readings usually every metre. And what it's doing is it's then looking at the difference as it passes the charge through the ground between the difference between the 2 remote probes and the 2 fixed probes. And if you've got something like a wall, the electricity will struggle to pass through it, so you get really high resistance. If you have something like a pit or a ditch, because of the organics held in a pit or a ditch, they're usually more moist, so the electricity passes through much more easily. So you can then produce a data plot from that. With resistivity, usually you can get readings to a depth of between 1 metre and half a metre. So it's not particularly deep penetration. And that penetration difference depends on the size of the feature. So if you're looking for buttresses in a church, they are going to be quite big, so you'll get a much deeper penetration and a deeper picking up, unlike if you're looking for a small pit. So there's lots of different types of resistivity meters you can get. So you can get frames, so like this Zimmer frame, but it's just got a longer array on the end. You can get quad frames, so these are where you don't have your umbilical cord, but you can put all 4 pins in at the same time. It does it internally. Or you can get a cart set up like this, so you've got probes on wheels, you can tow it along, and it will pick up the change in the ground. This also, you get much more denser readings. This will take readings every 5 centimetres rather than every half a metre. So, with all the techniques we're going to discuss, there are lots of strengths and weaknesses with the different techniques you can use. And it's important to understand these. So with resistivity, it's very good for locating walls, pits, ditches, things that have a difference in resistance. It's very good in urban environments. It's not affected by the urban environment. So I do a lot of community archaeology work. So we do a lot of work in village greens, in people's gardens, and it's not affected by any of that, unlike the other techniques. You don't have to be very skilled to use it, so because I do a lot of community work and a lot of work with schools, school kids can use it. It's very good for that. You don't need a very technical background to use it and set it up. It's a bit like a plug and play instrument. It's reasonably cheap to undertake. The survey equipment will set you back about £7,000, which is relatively cheap compared to a lot of the other techniques. And the data is pretty simple to interpret. We'll show you some data in a minute. There are some problems with resistivity though. It is affected quite a lot by ground moisture. So it won't work in very wet environments. So like at the moment when it's rained a lot, you'll just have a very white survey because it's so moist, there is no difference in the electrical resistance between pits and ditches and the background. You also, though, can't do it in a very dry environment. So a few summers ago it was very hot and dry. You'll have the opposite problem. There is no difference in ground resistance, but everything will just look really dark on the survey. So you won't be able to see walls as well, or pits and ditches, because they haven't got that moisture within them. It doesn't work on clay environments. Clay acts like a sponge. It is either really wet or baked rock hard. So you have problems with interpretation of the data. It's affected by the weather, which we've discussed. Geology. With resistivity, if you've got a very solid geology and you're looking for walls, and you've got very high geology, so like chalk, the geology will show on the data, and they can look like walls and floors and surfaces. So depending on what that geological type is may depend on the quality of the data that you're producing. You usually only get a single plane of data, so you only see a single flat plane of data. There is a technique you use to get what's called alpha and beta data, so you've got top and a bottom. It doesn't use a huge amount, unlike some of the other techniques where we can get more than one plane. Doesn't work in thick vegetation. You're fixed to an umbilical cord. It's 60 metres in length. If you break that umbilical cord, well, in regional stuffed, the technique's not going to work. So if you're working with trees and bushes and thick vegetation, you're going to end up getting tangled round and round. So it doesn't work very well. It's very slow. You can, with practice, do a 20 by 20 metre grid square in 20 minutes. Unlike the other techniques, that is pretty slow. And that is only with practice, so I can do that, but if I just gave it to one of you and asked you to do a survey, it would be maybe half an hour, 3/4 of an hour, which makes it quite a slow technique to do. There's no immediate data feedback on it either, so you can't see the data. You get little numbers, but that's about it. You can't see the data until you post-process it, and the equipment's quite bulky. You've got a frame, you've got cabling, pins in the ground. If they unplug, your data is ruined, so you have those problems. So this is a data set. So this is a data set from St Elizabeth's Chapel, which is on the outskirts of Winchester, the survey I did. So on the data set, there's a grayscale image. Anything in black is high resistance, so more likely walls, and anything in white is low resistance, so pits, ditches, things which hold more moisture. So hopefully you can all see this nice big high resistance feature in the middle. Yeah. So this is the chapel. This is St Elizabeth's Chapel we were looking for. It's made of big stone walls, so it is very easy to see. It is really high resistance. This nice linear feature running through here, this is a sewer pipe. Because it's full of water, the electricity, and it's steel in nature actually, the electricity passes through it really easily, so it's very low resistance, shows in white. And it cuts nicely through the end of this wall, you can see. We have a nice record for that actually, of them actually having to use dynamite when they put this sewer pipe in. There's also other features, so you can see divisional walls, and possibly other buildings, and other big high resistance features on the survey. So it is, within reason, pretty easy to interpret. You can see the walls, you can see the low resistance features. Now, I said there was a problem with water and the amount of ground moisture. This shows the seasonal effect that seasons change on a survey. So this survey was done every month through 1989 into 1990. And it shows the changing nature as the ground dries out and becomes more moist. So some of these features, like these high resistance features, become harder to see in the summer months because the ground is drying out, as well as these low resistance features, these ditches, which also become harder to see because they are as dry as the surrounding ground. So with resistivity, if possible, you need to decide when you're going to carry out a survey. If it's best to do it in the winter months, or if it's best to do it in the summer months, and how wet or how dry that ground will be. Okay, moving on. We also have electrical resistance imaging. This works a bit like resistivity. It's in that same category, but is slightly different. So you have probes, the same as resistivity, but these are all fixed. They are put along a tape line, and you put the probes in at set intervals, and you pass a signal through the probes as sets of 4. And it produces a deep cross section. So you get deep penetration. So you get data that looks like this. So you have nice deep penetration, so this is going down 2 or 3 metres, 4 metres into the ground. However, because you are having to put lots of probes in the ground, it is very slow. So you'll get a slice through the ground. You then have to pick all the probes up, move them along, put them all back in the ground, repeat the process. So you only get these slices of data. So it's very good if you're looking for something very specific and quite deep. So in this case, it's a tunnel. So this is a very low resistance feature. So you can see it, because the air in it, the electricity passes through it very easily. So if you're looking for cellars, things like that, but you need bare earth. You can't put it in this floor. Okay. Fluctuate radiometry is the next technique. So it's also known as magnetometry sometimes. There is a very slight difference. It's also produced by Geoscan. There is also another company called Bartington. They also produce the instruments we use. And it picks up the change in the local Earth's magnetic field. So you have a worldwide magnetic field which is being produced out of the poles, but we don't want to look at that. We want to look at what's very local, and it changes because of the underlying archaeology and the geology. So there are different types of magnetometers you can get. Magnetometers in general measure the change in the Earth's magnetic field, measure in SI units, and there are a measurement of Tesla. Now, we don't want to look at Tesla because that's a huge unit of measurement. What we want to look at is a very weak signal being produced. So if a pit has got charcoal in it, that produces a very weak magnetic signal. So we take measurements in nanotesla, so 1,000th of a Tesla. Now there's 2 techniques you can use. Use what's called argon vapor magnetometry. So this measures the total absolute magnetics of an area, a given area, of a local magnetic field. It's quite difficult to use. It can be quite time consuming, so not many people use it. It's also quite difficult to calibrate. Most people use fluctuate gradiometry instead, much easier technique, and it measures the relative difference in the magnetics compared to 2 sensors that are usually separated between ½ a metre and a metre apart. So in general what that means is you have this thing that looks like a pole, you have a sensor at the top, you have a sensor at the bottom. As you walk along, the instrument automatically takes readings. We usually take them at 0.25 metre intervals. And then it takes both readings and it calculates the difference. So in this point, it's 0.7 of a nanotesla. It's quite a quick technique to do because it automatically takes those readings. Lots of different instrument types you can get. So you can get dual sensors, so you can do 2 lines at once. Most universities use this type, so you can use one. It's much easier to use with students. You can hook up to the cart, like you have the resistivity, which means you can then take resistivity and magnetometry data at the same time. And you can always use big arrays, so big multi-arrays like this that are topo. These were used for things like the Stonehenge surveys, to do big environments. You have strengths and weaknesses with magnetometry. So magnetometry is very good for locating pits and ditches, kilns, hearths, brick buildings. It needs to be able to produce a magnetic signal. So that's either through charcoal or heating up either of the ground or of the material it's made of to change that magnetic signature compared to the background. It's very good in rural environments, so fields, big open areas we like with it. It's pretty quick to undertake. You can walk a grid square, 20 by 20 metre grid square in less than 10 minutes. The instrument also sets the pace for you, so it will tick and you have to walk on that pace because the instrument doesn't know where it is in time and space. You get very high resolution imagery, so we take readings every 25 centimetres. Unlike with resistivity, you'll only take it at metre intervals. It's relatively cheap. It's more expensive than resistivity, but much less expensive than radar. A magnetometer will set you back about £15,000, something like that. And it's single operation. You only need one person if you're well practiced at magnetometry. Just walk up and down between posts. With resistivity, you need a minimum of 2 people to be able to do it because of the cable. There are some quite technical problems with magnetometry. You have to be totally metal-free. So all your clothing has to be metal-free. So I have a set of clothing that I use only for magnetometry. So that's no buttons, no metal zips, no cleats in your boots. If you've got a hip replacement, it will pick that up. A pacemaker, even the tiny screw in your glasses, it will pick up. It is really sensitive to background metal. If you've got a pen in your pocket, it will pick the spring up. And if you've even got a tiny bit of metal in you, what you'll end up with is a survey data that looks like a barcode, because it will just strike with the metal that's in you, or on you. Because of that, it's not very good in urban environments. Fences, cars, overhead power lines, even aircraft going over the top. I carried out a survey in the New Forest. The police helicopters decided to fly traverses up and down our survey area, very low, because of the spinning rotor blades that produce huge magnetic survey signals and wrecked all our data. Igneous rock, so that has its own magnetic field. So you can't survey using magnetometry because it will just blank everything else out. It's too magnetic. You can't use it in thick vegetation because you're walking on a pace, the same as you can't use it on a steep slope as well, because you've got to walk on that pace. If you fall over or whatever, you just stop and start again. You only get one slice of data. You can only ever get one single slice of data with it. There's no immediate feedback, so you get flicking numbers going past, which you won't be able to see because they flick past really quickly, so you have to post-process that data. It also attracts lightning, which is a slight health and safety problem. The protocol for it is put down the magnetometer and run away, because it is quite hazardous in that nature. Now the bottom one, mobile phones, this depends if it's a strength or a weakness, depends if you're a student or a member of staff. I think it's a strength because it means that the students have to put down their mobile phones because they're physically attached to them, it seems. Because mobile phones produce a huge magnetic signal. When a mobile phone rings, it produces a huge magnetic signal and you will see it on the data. Now the students that I teach might think it's a weakness because they have to put down their mobile phone and turn it off and keep it away. So that's a problem. Now this is nice, it's a magnetometry plot. This was done by some colleagues of mine at Oxford University. And the things in black and in white are high and low magnetics. So hopefully you can see, so up here there's lots of ditches. Because of the charcoal in them, they produce huge magnetics. Really nice dark magnetic features. This space down here, this is a pylon, but this also produces huge dark magnetic signals. And because it's bigger metal, you produce a shadow on your data, which will mask the underlying archaeology. Running through here, you get what's called a bipolar feature. So this is a feature that's both really high magnetic and really low magnetics simultaneously. And it's caused by an buried electrical cable. And you'll see modern services really well on magnetometry data. Gas pipes, water pipe mains as well show up really well. You can also see old trackways, and this is a nice amphitheatre. So it's actually stone, but it shows on the survey data still. So the other technique we're going to discuss is ground penetrating radar. This is a newer technique. It's only been used in archaeology in about the last 20 years. You get lots of different frequencies of sensor. So at the university, British University, we mainly use 4 types of sensor. So we use high frequency sensors. So these are 500 and 250 megahertz. So a 500 megahertz sensor will penetrate into the ground about 1.5 meters. A 250 megahertz sensor will penetrate about 4 meters. And it looks like this. It looks like a bit of a small cart. You have a receiver and a transmitter and an odometer wheel for distance. A low frequency sensor, so a 100 megahertz sensor, will penetrate about 10 to 15 metres, and a 50 megahertz sensor will penetrate about 25 metres. High frequency sensors give really good resolution. So they're used a lot in archaeology. They're also used in forensics, so if you've got a clandestine burial, someone's buried their grandma under the patio, they might be using a high frequency sensor. Low frequency sensors like these here, that look like ski boards, these don't give very high resolution but give really good penetration, so they're used more to look at sediment change or to look for caves or different rock formations, geological rock formations. So we don't use them so much in archaeology but more in geology and geography. So how does it work? It basically works the same as airborne radar, but we're not looking for planes in the sky, we're looking for what's buried under the ground. So we have a sensor which has a transmitter and receiver, so the same as airborne radar, and we're sending a signal through the ground, so a radio signal, into the ground. It bounces off the underlying sediments, the underlying material, reflects back up and gets received by the receiver. And then it will calculate the time difference between sending and receiving, and it can then work out the depth of the item and how hard it is, how solid it is. It will take measurements in megahertz, and it will take measurements, so ours takes measurements every 2.5 centimetres and takes 32 readings per 2.5 centimetres. So you get a very detailed image of what's under the ground. You also get data in two types, so you get grayscale and colorized image. So you get what's called pseudo-sections, so if you think about slicing through a cake, you'll see the sponge and the jam and the cream and the sponge. But we'll also get horizontal slices, so it's like slicing off, taking off the sponge as a layer and the jam as a layer. There are lots of different types of radar equipment out there. There's lots of companies who produce it nowadays. We get ours from Canada, from a company called Central Software, and you can do lots of different things with it. You can put it in front of a vehicle to use multi-spectral imaging, multi-scan. You can even fit it to a drone. There's some companies looking at drones, looking at surveying for underground services, so water pipes. You can put it down boreholes. You can look at building structures, so this is a base pillar of a bridge, to look at the makeup of that. It's a very good multi-purpose piece of equipment. But there are strengths and weaknesses, like the others. So it is very good for locating walls, floors, graves, pits, air voids, sedimentary changes. There is lots of different things you can find with it. It can be used in all weathers, so it's not affected by the weather, within reason. You can even use it on snow. It's used to map ski slopes in industry. So you can use it in different things. Use it in water as well, so you can put it on a boat. And it's been used to look for Roman bridge pillars over a river before. It can penetrate solid surfaces. Magnetometry and resistivity, you need bare earth, and most geophysical techniques you need bare earth. Ground penetrating radar will penetrate solid things. It will penetrate this floor, it will penetrate concrete, tarmac, pretty easily. So it's very good for urban surveys, for inside buildings as well. You can get really deep penetration. So you don't get that single slice of data, you get lots of slices of data. We usually slice at 10 centimetre intervals to the base of the data set. And you get multiple slices. So you get on alpha and beta planes, so you've got X and Y plane data, and you can produce 3D imaging then from that. you get live data feedback as well. So you have a logger, so like a TV screen, and you'll literally see that slice through the data in front of you. So if you want to specifically map buried services that's used for in the utilities industry, you can actually map those on the ground as you work. You don't have to go back to the office and post-process that data. And it is really quick to undertake. You can drag it behind a vehicle, you can walk with it, run with it. You're not stuck with survey grids. You could have, your first line could be 0.5 metre long, and your next line could be 2 kilometres long. Because it's got an odometer wheel with it, it knows the distance you're travelling. And you can link it to GPS as well. So it knows where you are in time and space. There are some problems with it. The equipment is very expensive. The equipment we have is £50,000 and it comes from Canada. So trying to get things fixed is a problem with it as well. It doesn't work on clay geology. Clay acts like a sponge to radar signal. So it will send the radar signal into the ground, but you won't get any reflection back. It just absorbs all that signal, so you get no penetration. You have the opposite effect with reed bars. So this is bars that you find in reinforced concrete. This also occurs with underfloor heating we found recently. So the the instrument will send out a signal, because reed bar is so dense and underfloor heating pipe is so dense, it will just reflect all the signal back and you get no penetration into the ground. So you just see that reed bar in that concrete. The other slight health and safety problem you have is that it can set off buried unexploded ordnance, so bombs. So it's not very good to use in London or urban areas or Southampton docks, anywhere that was bombed during the war, because you don't want to blow yourself up, particularly. So the data you get. So I said you get 2 types of data. So this is the pseudo sections or cross sections through the data. So these are from a church that I surveyed in Oxfordshire. So what you can see is this is metres going down. So we go 3 metres into the underlying archaeology. You can see the floor surfaces at the top. And this is the underlying geology. In this case it's limestone. And then you can see, so you've got a wall here, it's a nice thick wall, and there's one here as well. You can see how far they are under the floors. You can also see in here, so this here is a grave, and these funny crisscrosses are where the signal is bouncing around the inside of it because it's hollow. So this demonstrates to me there is an air void there. So we can show the different types of sediment patterns as well. We also have time slices, so we can slice horizontally through the data. So you get an orientation of a church. This is the aisle, this is the nave, and this is the chancel. So because we can slice out 10 centimetre intervals and get multiple planes of data, we can see through the data of what underlies each other. So this is, the top image is 20 to 30 centimetres down. So you can see this high reflective feature. These are the heating pipes that run under the floor. So if we were doing just resistivity, if we lifted the floors and just did resistivity, that is all we would see, because it would mask the underlying archaeology. Because radar, we can penetrate much deeper down. At this 1.5 to 1.4 metres below current ground surface, we have a building in here. It's a Saxon church, stone church. But we can also see the 12th century stone walls where they were pulled down when they put the aisle in. You wouldn't know this was there without radar, because somebody will complain if I started digging the church floors up, but the radar will penetrate them and can see what's below in the underlying archaeology. These are using high frequency sensors, so this is good resolution, so this is 250 megahertz, but also good penetration. It's an example of where someone's used a low frequency sensor, so they're most likely using a 50 megahertz or possibly a 10 megahertz sensor. They were looking for a B-17 Flying Fortress bomber in Greenland. It crashed in 1942, So they're penetrating through ice sheets. This is a time slice through the section. So you have, this is snow build-up and ice, and then you have this feature at the bottom which they thought was the aircraft. So they dug a hole and they found it. So you have these, you can use deep penetration radar, not just on Earth but in ice as well. And this is the aircraft they found. So we've got all these archaeological techniques. We use them a lot of the time individually, but you can also use them as combined techniques. So you can survey the same site using all the techniques. So this is a project I worked on with Leicester University, looking at long barrows, so Neolithic long barrows. We used all the techniques for all the long barrows. So we've got, this is topographical data at the bottom. So this is an earthwork survey, looking at it. This is the radar data. It's quite hard to see on this image, but you can just about see the ditch that goes around the outside bit. This is magnetometry data. Now the magnetometry data, you can't really see the ditch. You should be able to. What you can see instead are all of these high magnetic features. These are concrete posts put in my English heritage to show the edge of the monument. So it wrecks the data because they've got reinforcing bars in them. So if we just did magnetometry, we wouldn't really see anything. And at the bottom, this is resistivity, so you can see the edge of the mound, but you can also see the edge of the ditch that goes around it. So you can see how different techniques used in different areas, in the same area, can show different things. Now, moving on, looking at other things. So another area we use non-invasive surveying is nowadays is 3D laser scanning. So this can be used, you can get a terrestrial scanner, so this is made by Leica Geosystems. So for scanning buildings, this was one I did of a church, it's a project I run. But also using airborne scanners, so LiDAR, so light directional airborne ranging, directional ranging. But it's mounted in an aircraft. You fly over, so you fly traverse. It's a bit like flying with aerial photography, but instead of taking photographs, got a scanner, and it's bouncing off the ground and it's picking up, and it knows where it is. It's done by the Environment Agency. You can access the data free online. Anyone can access this data. It's mainly done for flood prevention works. So if you're in an area of flooding, you get better data. And they'll usually take data in meter resolution. So you get meter resolution on the X and Y axis, and sub-centimetre resolution on the Z axis, which you're using lasers. The terrestrial laser scanner, so one for scanning buildings, we're getting 3 mil accurate data. So we're getting extremely accurate data. For looking at buildings, it is brilliant. It's much easier. If we did a building survey by hand, let's say of this room, and measured in all the light fittings, all the screws and everything else, it would take us hours. Stick a 3D laser scanner in the middle of it, one scan would do it. It would take less than 5 minutes. You then post-process that data, and you've got a model of what you've got. So an example, this is St Denis Church at Stamford Vale, where I carried out quite a big research project. We laser scanned the whole church, inside and out. It took us about half a day, 3 mil accuracy. So we put it in some software. You can produce 3D models. You can slice the data, so we can get floor plans, looking at wall thicknesses, and you can also slice it horizontally, so you can see how rooms relate to each other and the changing nature of buildings. This is a section through the chancel. What we never knew about the chancel until this point, if you look at this wall, nice upright wall, this wall, not so much, and it's sloped by about 5 degrees. It's most likely sinking into the Saxon ditch, but no one had noticed this about the church in the modern period anyway, and we think it stopped sinking, I hope. LiDAR data, so this is also Stamford Vale. So this is a LiDAR image. This is taken by Airborne. It's the Environment Agency data. Now, in the middle of here, you should have a village, but there isn't one. So this is why it's quite good about LiDAR data. So unlike aerial photography, you can just see what's on the surface. So if there are trees masking it, if there are buildings masking it, that's all you're going to see. LiDAR data, it will penetrate the trees in most cases, apart from you, which it doesn't penetrate because of its density. We can then take that data, we can put it through some computer algorithms, and it will strip off all the vegetation, and it will also strip off all the housing as well, and anything modern. And because of that, you can then see the underlying earthworks. So you can see there are field systems down here. These are medieval and Celtic. You can see these are blast walls from the Second World War. This will take hours, if not months, weeks, to survey by hand. But we can make these computer models. An example of what you're going to see, so the right-hand image this is aerial photography. So this is aerial photography of Stamford's DMV, so a deserted medieval village. Now, with an eye of faith, you might be able to see a trackway running through here. That's about it. This is the LiDAR data of the exact same area. On here, you can see trackways, you can see building platforms in here, land divisions. Without LiDAR, someone would have to go out by hand with a drawing board and map these. With LiDAR data, we can do it in-house using computer software, and map these much more accurately. And it's a much more accurate way than aerial photography even.
The parallel lines, ridge and furrow ploughing.
These parallel lines.
The multiple lines.
These ones.
Like barcodes.
Yeah, this is ridge and furrow ploughing. Yeah. Just
The old
ploughing.
medieval.
Yeah. Yeah. So it's picking that up as well, and you can even see 3 or 4 phases of field system. We've got earthworks because the accuracy of the z-axis is so much. You can pick up multiple phases that you won't see on aerial photography. So we've talked about resistive geophysics, and we've talked about LiDAR, and I'm hoping this will work. So this shows resistive radar and laser scanning being used in our environment, combining the techniques. So you've got a 3D laser scanner on top, so you produce 3D laser scanning imaging of London, centre of London. Not closing roads, producing this high quality 3D data, mapping data, but you're also producing what's on the ground, in this case buried surfaces, utilities, but that could be walls. This has all been done at road speed, so not needing to close roads, not needing to dig any holes, being able to map the urban environment and where it relates to each other. Using GNSS, which is GPS signalling. So new techniques are coming in. So we can do geophysics, radar in this case, at the same time as collecting LiDAR data and laser scan data, all behind a vehicle, all at national road speed. It's also being used on the railways to map high voltage power lines. So we're using more techniques, more computerised techniques, rather than doing things manually. Now, the last thing we'll talk about is how do we know what we are finding through geophysics or through laser scanning, etc. How do we know that is definitely interpreted right? So we have to, in the end, dig a hole, do something called ground truthing. So the photograph here, this is a piece of resistivity data that I carried out in Stamford Vale. You can see there's some high resistance features. There's one up here. And there's also a nice square one down here, inside this low resistance feature, this white area. Now when we carried out this survey, we knew there was a village pond at the bottom, that it was backfilled. It was definitely, there's a record of it during the medieval period, and it looks like there's a nice building over the top of it, nice square walls. So we dug a trench over the nice square building and found this. It's a dump of 1950s rubble. So our interpretation of it being a nice building is incorrect. But the only way we'd know that is by digging a hole. In the end, it will come down to excavation. We don't always interpret things right through geophysics. You still need to look at what it is. It is just a dump of demolition rubble from the adjacent school, in this case. The last one of the drowned tree thing, my last slide, because I quite like this. This is some survey work that one of our students did, just outside Newbury. It was meant to be, it's a known Roman site, so it's known to be, it's meant to have a villa there, there's some Bronze Age activity as well. They did it across their school playing fields, and all they found was their school playing fields. What you've got is multiple phases of football pitch. So you've got the centre circle and all the goals at either end. There's one down here, and it masks all the geophysics. This is resistivity data, so the white lines are holding more moisture than the underground lying ground. So it's also an importance of knowing what was there or what is there currently. Okay, that's all I have. Thank you.
Question, please.
As a answer them a little bored or senseless.
I'm aware of Kinetic, the defence contracting people, have got a system for a FLIR system of infrared camera system with a resolution of 1/10,000th of a degree C. You have to use it at night to survey areas. That's not come into the archaeology world. If it did, would it be any use, do you reckon? Be able to resolve that sort of thing?
We do use some thermal imaging, you use some satellite thermal imaging, but a lot of things with archaeology is cost. As things come down in cost, it's more likely to be used in the archaeological world, something like that would be horrifically expensive. That's why radar is being used a bit more now, because the cost has come down. And as it's used more in other industries, then it will be developed into archaeology. Same as laser scanning, it used to be horrifically expensive and horrifically time consuming. The cost has come down and the instruments have got better, but the cost has not got worse, so they're used more. So it's always a cost benefit things. We use them more in research because we don't have the cost problems so much. But in a commercial environment where you're building houses, the cost is a problem. The way things are done or not done.
I think it was last summer, we had a hot spell with no rain, and I think on the BBC website they showed you some aerial photographs. I came in a bit late, did I miss that? Was that
so aerial photography is good. It's very good in very dry environments. So when we had a really hot spell in the summer, because aerial photography, so the items, so ditches, pits, buildings show really well, because when you've got a crop on, things like pits and ditches, like resistivity, it holds more moisture, so your crop will grow taller in dry environments, and the rest of the crop will be much shorter. The same if you've got a building, because it's a wall, it's much drier, so the crop will grow shorter again. So you can see things in crop marks. The same in grass, so they're called parch marks. So you have, you can see them. So I've been working on a project at IBM in Hursley recently. they have, in the same hot summer, on their grass lawn, they can see the old Tudor Hall that was pulled down because the grass turned brown and died where the walls are really close to the surface because there's not much moisture, but the green grass round it, where there was more moisture, grew a bit more. So you can see that underlying archaeology. But you need that contrast. If it rains lots, all the crops are going to grow, all the grass is going to grow, and you're going to have no contrast.
Well, like satellite imaging, we had a lecture last month about that, and it sounded as though it would be useful in archaeology.
So we do use satellite imaging. Resolution is a problem. So unless you're using really high resolution satellite imaging, or if you're looking over big areas. So it's used a lot in areas that are inaccessible. So the Sahara deserts, places in Egypt, where people are mapping archaeological sites through satellite imagery. But somewhere like the UK, because we have very high resolution aerial photography, we would use that more than satellite imaging. Unless you're trying to do something very specific, like look at thermal data or multispectral light sourcing data, you may use satellite imagery more than you'd use aerial photography.
Things like sinkholes that we hear a lot about these days, is LiDAR any good for just flying across areas and old mine shafts and things like that?
Depends how well they've been capped. If they've been really well capped with bits of concrete and the ground is not sinking, then you're not going to see it. If though it is sinking, you will see that contrast difference. You'll see that dip, that depression. The problem with a lot of mine constructions is that they very suddenly collapse. Because the shoring goes, or there's water penetration and anything, and the material around it just gives out suddenly. So it can be literally a split second from being a nice flat ground to a sudden drop. So it's one of the problems if you live in areas with lots of mine workings, and they're not very well mapped either in most cases.
If you had to survey in the summer months, resist the survey, I take it there's no point in bringing a bowser of water in and spraying the ground.
No. Some colleagues of mine did a good example of resistance problems. A colleague of mine did a survey in someone's garden, nice big garden someone had, and when they came to post later, it had a nice square in the middle of it. They wondered what this square was, and they spoke to the landowner, and it turned out the week before they had a tent pitched. And it rained heavily. The ground around it was nice and moist. The ground where the tent wasn't so much, even though it rained in between. And it's the very slight difference, because it's only looking at really slight difference in ohms measurement in a decimal place. So that very slight change will give you very slightly different earth resistance readings.
Actually, you said that the LiDAR data was publicly accessible.
Yeah.
Is there anything useful we could do with it at home?
You can use pieces of, so you can download the data, you can look at it online, you can view it online. If you download the data, you can use a piece of software called QGIS, which is a free GIS package. There'll be some instructions online also how to use it, and you can then manipulate that data if you want. Around here, so for the Southampton area, because it's coastal, you're likely to get actually higher resolution data. You might get a ½ metre or 0.25 metre, because it's also used for flood prevention works from coastal erosion as well. So, yeah.
Well, there's a chap at Southampton University, I think other places have done it, but he's got some software for automatically estimating where solar panels can be put, and the shading and all this sort of stuff as well.
Yeah, so we use ArcGIS, which is a package we pay for. Yeah, we can move the sun round, and we can, so that's how we can look at LiDAR data very well, because we can manipulate where the sun is and where it sits and where the earthworks are to be able to see things. So I expect that same sort of package he's using to do that.
Actually, with all this technology, are there any big discoveries to be made, or is everything sort of done quite?
It's we have all this technology, but it's knowing how to use it and where to use it. New discoveries done all the time. So I worked on a project about 5 years ago in the New Forest. The New Forest is known to have no Neolithic causewayed enclosures. So a Neolithic causeway enclosure is an enclosure, a ditch enclosure with lots of spaces in it. And there were none known about the New Forest. We did some radar survey, and when we did some excavation, we found one. And that's because there's been a big LiDAR project in the New Forest. They found lots of hill forts, so the trees are in the way. But we penetrated with radar what looked like geology. It was sand, pure sand. Everyone had thought it was the geology. The radar penetrated that, and we could see the causewayed enclosure underneath. So it matters how you use this technology. We did resistivity magnetometry as well, but you couldn't see it on those, only because the radar is penetrating that sand deposit, could we see it. But because of the cost of the technique, it's not going to be used everywhere, because it's very expensive to undertake.
Is it expensive? You said the equipment is expensive. Is the operating cost expensive as well?
If you, the operating cost, if you hired someone out to do it, because of the equipment cost and the software licensing costs, it would be expensive to then hire someone out to do it, or to pay for someone to do it, because it's got that knock-on effect, because someone's got to pay for the equipment. For us, it's research, so the university's paid for the equipment, so we don't have that cost problem so much. But if you were doing commercially buyers building houses, then it's got a cost implication because of licensing of the software, etc. And the time. It's quite quick to undertake on site, but then the post-processing of that data is quite time-consuming, and then the interpretation, because you've got loads of data. It's the same as laser scan data. Everyone went through a phase, it's slightly reducing now, of going, oh, new kit, oh, this new laser scanner, we're going to scan everything. But you produce huge amounts of data, gigabytes and terabytes of data from a single scan. What are you going to do with it? Why have you done that scan? How are you going to manipulate that data? And have you got a PC actually to be able to physically do it? So it's knowing what to do with that data. You might be able to collect it all, but unless you have that expertise of how to interpret it, it's not really any good to anyone.